Good morning, students. Once again, welcome to our class, that is Data Communication and Networks. And we are going to see last chapter in first year, that is analog transmission. Analog to analog or analog to digital transmission. So here only we are seeing analog to analog transmission. But before going to evaluation, first we have to check where analog to analog transmission is necessary. When a signal that has that is released at the receiver, that is sender station. You can take an example of television channels that has been released at a relay station existing at metro cities, and we are receiving those by existing at home through our televisions or mobiles or any other etc. So here the signal that has been released at the relay station in form of analog. When we are receiving as the receivers at our home, the same analog signal that has been converted into digital and received and reproduced in the same format in the receiver system. That may be any system. But here, when the signal that is released, whether that is existing in the same format or that cannot, whether that can transmit through the longer distances without any disturbances, or it has been having the same distance. These are the questions that can be raised. So analog to analog transmission is producing, that is resulting the outcome to these systems. When an analog signal is released at the sender station and released into the wave for transmission, that should travel miles of distances to reach the receiver. So when the signal that is transmitting through air as the carrier, air is also in analog format that may combine with the released signal. And there may be number of noise disturbances existing, and those may also in analog format, those also may be combined with the signal. And these are the number of disturbances. And second one, when the signal transmitting or travels longer distances, automatically it can lose its strength. You can see when we are focusing the light, near objects we can view, but far objects are not visible. That is, the light ray strength is large when the object is near. When that travels longer distance, the strength is less. So similarly here, when the signal travels longer distances, it can lose its strength. For this purpose, we are using towers are nothing but the amplifiers for analog signals, which are having the capacity of receiving large volumes of analog signals and amplifying the signal and reproducing it. So this is necessary for an analog signal to reproduce in same format in which that has been released at the sender station. For that purpose, analog to analog transmission is also necessary to us because that needs amplification. Re-strengthening. Amplification means re-strengthening the signal in the same format by demodulating the signal, removing the external disturbances and reproducing the original signal in the same format. This is nothing but amplification. So for that purpose, here we are going to see how can we allow the modulation in analog signal. Modulation is nothing but amplification. So here, well, already we see in first class, for an analog signal, there are three characteristics: amplitude, frequency, and phase. So we can use these three as measures for amplification or modulation. So analog to analog conversion is the representation of analog information by an analog signal. One may ask why we need to modulate an analog signal. Already I told what is the reason for modulation. It is already analog. Modulation is needed if the medium is band pass in nature or if only a band pass channel is available. That is, amplification is compulsory due to the problem that has been stated earlier, or the signal is a band pass. Band pass signal means here that has to be converted again into a digital format for receiving at the receiver station. That is nothing but band pass. So for that one here we are using three different types of modulation methods. Amplitude modulation, frequency modulation, and phase modulation. Analog to analog conversion consists of three different types of modulation: amplitude modulation, frequency modulation, and phase modulation. Amplitude modulation. A carrier signal is modulated only in amplitude value. The modulating signal is the envelope of the carrier. The required bandwidth is double than the bandwidth, where B is the bandwidth of the modulating signal. Actual bandwidth is B and the reproduced bandwidth is double than the original bandwidth, half for transmission and half for receiving. Since both sides of the carrier frequency FC, the spectrum is identical, we can discard one half, thus requiring a smaller bandwidth for transmission. That is, if both sides are identical means one way we can discard half. If that is dual mode, we can consider both. So this is how can we use the amplitude modulation. This is the original signal and this is the carrier frequency. We are combining with the original signal. That is, you can see why we have to use. When we are taking a wire, if that is very lean, easily that can be cut or cleared down. When we are strengthening that with 2 or 3 other wires, automatically that becomes very strong. And similarly, the signal which is released, if that is combined with a static carrier frequency, then automatically that will become strengthened. But when we are considering amplitude modulation, no need to consider the frequency, that is number of samples, no need to consider the phase, that is either positive or negative. Simply you have to consider amplitude, how the signal amplitude existing. Depending on that, you can combine the carrier with that amplitude value only. That is, the signal is in the same format, but the number of samples are increased. That is nothing but amplitude modulation. So, we are incorporating the carrier frequencies into the signal, reproducing that. For this purpose, here we are using an oscillator as a multiplier, multiplying this carrier with the original. Multiplier means not multiplying, similar to multiplexer in digital electronics. So, combining that with the original signal and reproducing with double the bandwidth. So, this is the amplitude modulation. The total bandwidth required for amplitude modulation can be determined from a bandwidth of an audio signal, because amplitude modulation is always used in audio signal because this bandwidth is not insufficient for a video signal. So this is suitable for an audio signal. So bandwidth of an amplitude modulation signal is equal to double the bandwidth. So this is the frequency ranges, so always existing in kilohertz. 530 to 1700, we can divide those into simple 10 kilohertz frequency partitions. Next, frequency modulation. Frequency modulation is always used for audio and video transmission, because this is always having a bandwidth 4 times than the original bandwidth combined with the signal, and also having higher frequency than the amplitude modulation, that is in megahertz. The modulating signal changes the frequency of the carrier But in frequency modulation, always we can consider only frequency. Amplitude and phase become static. In amplitude modulation, amplitude is varying, frequency and phase become static. The bandwidth for frequency modulation is high. It is approximately 10 times the signal frequency. So already we have seen in kilohertz in previous one. Here that is megahertz. So the total bandwidth required for a frequency modulation can be determined as bandwidth of frequency modulation equal to 2 into 1 plus beta into b, where beta is commonly we can consider as 4. 4 times greater than the original bandwidth, because we are considering in frequency amplitude modulation we are considering partitions of kilohertz, but here 10 times greater means 100 kilohertz means automatically the frequency range can go to megahertz. So in frequency modulation here we are not considering the amplitude, we are considering number of samples only. But all are reproduced with the same amplitude, because amplitude, value, frequency is altering. Here you should focus on frequency only. So the sample is reproduced with the number of frequencies, maximum at the higher amplitude and minimum at the lower amplitude. So the signal consists of the same format. Here the number of samples are very high at higher amplitudes, representation of the before modulation signal, and low at the lower amplitude. So here we are using voltage controlled oscillator that can produce frequency, carrier frequencies. That is voltage controls means here why we are using voltage control now instead of oscillator means oscillator always produce constant frequencies for combining with the signal. But here the frequency should vary. If the amplitude high, frequency should be multiples of 4. If the amplitude is low, that should be less than that. So for that one here, voltage controlled oscillator can reproduce the signal. Can produce the number of samples depending on the amplitude. So for that purpose here, we are using voltage controlled oscillator instead of normal oscillator which is static. And the frequency of this one is same, 2 into 1 plus beta. So here we can consider, in previous one we are considering 10 Hz, here 10 times greater than 200 or 100 kilohertz. Automatically if the number of partitions are same also, the frequency can go to megahertz. Last one, phase modulation. The modulated signal only changes the phase and frequency and amplitude. Frequency and amplitude are static. The phase change manifests itself as a frequency change, but the instantaneous frequency change is proportional to the derivative of the amplitude. So here we have to use the derivations because this is the angle of orientation. The bandwidth is higher than the amplitude modulation, but approximately equal to that. So here we can phase change. So when the phase that has been altering very high, then the frequencies are high. If that is continuous, frequencies are normal. When that is again altering from positive to negative, then the frequencies are again that can be changed. So here the frequencies are represented in normal state when the signal is in the same voltage representation. And when the voltages are changing, automatically signal orientation is changing, then the frequencies are maximum. In other situations, frequencies are minimum. So, voltage controlled oscillator also, similarly here also we have to produce because the frequency samples are varying minimum to maximum. If positive maximum, positive to negative or negative to positive, then we can produce the maximum number of frequency samples. If that is static, then the frequency is similar to amplitude modulation, no change. So here also we can consider similar to amplitude modulation. Bandwidth of phase modulation equal to 2 into 1 plus beta. But where beta is 2, automatically that may be approximately equal to amplitude modulation. So total bandwidth required for phase modulation can be determined from the bandwidth and maximum amplitude of modulating signal. Bandwidth of the phase modulation equal to 2 into 1 plus beta into B, where B is 2 most often. So, commonly we can avoid phase modulation. Always we can consider frequency and amplitude. Frequency modulation for an audio and video signals, amplitude modulation only for audio signals because that cannot acquire maximum band. So these are the different types of analog and digital signals which are allowing modulate analog and digital signal, that is analog to analog signal modulation using 3 different types of modulation techniques. So this ends up to the first unit, and we can go to the next unit, that is data link layer or media representations which we are using for carrying the analog signals or digital signals different types, either wireless communication or wired communication.